Okay, good morning all of you. Let's get started. Any questions from yesterday's class? Once again, this is the problem that we looked at in yesterday's class. Okay, using finite element method, and we solve this problem using variational approach, and this is the equivalent functional that is obtained, and this equivalent functional, to further simplify this, we adopted a finite element method. We discretize the domain from 0 to 1 into number of elements. Okay, and then we looked at how the solution converges if we adopt one element, two element, like that. Okay, so this is what the convergence plot is. So this is one element solution for this problem, two elements and three elements. And if you want, you can try four elements. And how do you choose four elements? This is two element solution, two element discretization. Whatever is shown here, this is a one-dimensional problem. So element 1 is taken from 0 to half, element 2 is taken from half to 1. If you want three elements, you can have three elements, not necessarily all the elements be equal length. Okay, it's not necessary all the elements should be of equal length, or if you want, you can try using equal length element. And one first, if it is three element, first element can be from 0 to 0.33, something like that, and 0.33 to 0.67 is second element, 0.67 to 1 is the third element. And you need to develop the trial solution for each of the elements separately, and then you need to write the functional taking into account all the three elements. And then accordingly here, the point where the boundary conditions are applied here, this is the boundary term, and so you need to see what node number corresponds to that location. So accordingly you need to use that. If you use three element solution, if you number the nodes like this, in this manner, this has 1, 2, 3, and if you use three elements, you are going to have 4 nodes. When you use two elements, you have 3 nodes. If you are adopting two node element, please take a note of it. If you are adopting two node element, if you use one element, you are going to have 2 nodes. If you use 2 elements, you are going to have 3 nodes. If you use 3 elements, you are going to have 4 nodes for two noded elements. Okay, so 4 nodes. So you can number them as 1, 2, 3, and one more node, 4th node. Okay, so this term, this boundary term corresponds to U4 in that case, and you may end up in getting this I. You may end up in getting I being function of more than here it is a function of 2 unknown parameters. You may end up in 3 unknown parameters if you use 3 elements. And after that, you need to apply the stationarity conditions and get the system of equations, solve them, and solve those system of equations to determine the unknown coefficients. Once you get unknown coefficients, you plug into a trial solution for each of the element, and you get the approximate solution. Once you get approximate solution in each of the element, you plot it in each of the element. Element 1 for 2 node element, for 2 elements, the element 1 is going from 0 to half. So this is going to be the solution between 0 and half to 1. This is the solution. So you can plot like that. So that is how this plot is applied. Similarly, derivative of u. Okay, same thing you can repeat even for 3 elements. And if you want 4 elements also, you can try and see how the solution converges. And why we are doing this? Because for real problems, we don't know the exact solution and we are trying to find the approximate solution. So in that case, as you increase the number of nodes, whether the solution is converging or not, and whatever solution that is converging, that you can take it as the solution for the problem. Okay, so this is how you can see the convergence. And I told you in the beginning, in the beginning classes, I mentioned to you that your trial solution, if you see the classical methods, the trial solution that you start, quadratic trial solution or cubic trial solution or quadratic trial solution or quintic. Quartic is nothing but 4th order, quintic is nothing but 5th order. Okay, and whatever trial solution you adopt, you need to include all the lower order terms, all the lower order terms in the basis function. So suppose you want to use 4th order polynomial, you need to have a0 constant term, a1x, a2x square, a3x cube, then only a4x power 4. Similarly, if you want to select 5th order polynomial, you need to include all the lower order terms. You cannot skip the lower order terms. If you skip the lower order terms, I told you at that time, I told you there is going to be some problem with your solution. So that kind of thing is going to show up here. When you miss the lower order terms, you will not see this kind of convergence. You can see here nice convergence is there from 1 element solution to 2 element solution, 3 element solution. Okay, so this kind of convergence you will not, this kind of trend you will not be able to see if you miss the lower order term. So that is one of the consequence of doing that kind of mistake. Okay, that you keep in mind. And this is the solution, and derivative of solution is this one. And you can see your solution is actually converging faster than the derivative of the solution. Still, after here, a 1 element solution is shown, 2 element solution is, 1 element solution is constant, 2 element solution is this one, and 3 element solution is this one. Still, you are not, if you see this plot alone, the second one alone, you will not get a feel that some convergence trend is happening, because derivative takes longer time for convergence. Okay, so that those points you keep in mind. So in summary, and first of all, why we did all this exercise, and if you had followed last 2 classes, whatever we covered carefully, then let's go and see why we started all this. We want to improve the classic, whatever solution that we get from classical solution techniques, we want to improve that. And also we want to improve upon the classical approximation solution techniques. And before we started all this, we noted 2 points here. The first point is, in classical approximate solution techniques, the trial solution is defined over the entire solution domain. Whereas in finite element method, we are going to discretize the entire domain into small pieces, and in each of the pieces we can use lower order trial solution, lower order approximation. So now, based on whatever we covered, you should be able to appreciate that point that we addressed. Okay, the first point is addressed. And in this, what is the second point? Second point is, in classical approximate solution techniques, the unknown coefficients A0, A1, A2, these are all mathematical quantities. They don't have any physical meaning. Whereas with whatever we learned in the last two classes, we brought some physical meaning to these unknown coefficients. We gave some physical meaning to these unknown coefficients. A0, A1, such kind of coefficients. Okay, so that is what all this is. We started with this kind of a trial solution, linear trial solution, and for a typical two-node element, what are the shape functions or interpolating functions, how they look like, that we noted, and also finally that u is equal to a0 plus a1x. Instead of writing in that way, you can write it in this manner. So this is all what we did, and by doing this, we gave some physical meaning. We gave some physical meaning to this these coefficients. You please take a note of it in your notebook. You please take a note of it. U is equal to a0 plus a1x. U is equal to a0 plus a1x, and if you want, you can actually take a note of this domain as well. You please take a note of this. Okay. And immediately after that, you take a note of this. U is equal to ni ui plus ni plus 1 ui plus 1. So now you compare both these equations. Wherever a0, a1 are there, they are replaced with ui and ui plus 1. Ui is nothing but the solution value at ith node, and ui plus 1 is solution value at I plus 1th node. So a0, a1 are replaced with ui plus 1. So a0, a1 are mathematical coefficients. They don't have any physical meaning. But whereas their replacement, we replaced a0, a1 with ui plus 1. Now ui and ui plus 1 have physical meaning. Okay. And one more thing. I told you to make a note of this equation. Immediately you take a note of this equation. Okay. So I want to compare both these equations. So now u is equal to a0 plus a1x, that is rewritten as u is equal to ni ui plus ni plus 1 ui plus 1. Just now I told you to make a comparison. A0, A1 coefficients, the corresponding quantities are ui plus 1. And what about the other one? What about the other thing? A0, what is the coefficient of A0? It is 1. What is coefficient of A1? It is x. 1x. In this equation, 1 and x, they are nothing but basis. They are nothing but basis functions. Okay, and what about this one? 1x are replaced. 1x is replaced with ni plus 1. So if 1x are the basis functions, similarly ni plus 1 are going to be basis functions. Ni plus 1 are going to be basis functions. So please make a note of it. Okay, whatever explanation I am giving you, you please make a note of it. Okay, that helps you to understand in long run. So ni plus 1 takes the position of 1 and x. 1 and x are the basis functions. Similarly, this ni plus 1 can be considered as basis function. Shape functions are nothing but basis functions. Shape functions or interpolating functions are nothing but basis functions. And what is the important property of a basis function? All the components of basis function should be linearly independent. 1x, x square, x cube, all these are linearly independent. And here, if 1x, their position is taken by ni and ni plus 1, ni and ni plus 1 are also linearly independent. all the shape functions should be linearly independent. In an element, finite element, all the shape functions should be linearly independent. You please make a note of it. Okay? Any questions? Let me see the comments. Any questions? So ni plus 1 are the basis functions, or they are the shape functions or interpolating functions. They are also basis functions. And ni plus 1 are linearly independent. Shape functions are linearly independent. One more important point. Here this equation, u is equal to a naught plus a1x. U is equal to a naught plus a1x. If it is Galerkin method, if you are using Galerkin method, what is weight function? Weight function is nothing but partial derivative of u with respect to the unknown coefficients. That is your weight functions. You are going to get so many weight functions as so many unknown coefficients. So here, if you take this one, if you take this equation, if you take this equation, if you are using Galerkin method, you are going to get two weight functions. W naught is going to be partial derivative of u with respect to a naught. W1 is going to be partial derivative of u with respect to a1. So please make a note of it. Okay. If it is Galerkin method. Now this equation, we have rewritten it. We have rewritten this equation as u is equal to ni ui plus ni plus 1 ui plus 1. We have written in this manner. And now you compare this to this a naught a1 position is taken by ui plus 1. And now, if you want to use Galerkin method, weight function. How do you define weight function? If you write in this manner, if you write your trial solution in this manner, how do you define the weight function? Weight function is defined as, for Galerkin method, partial derivative of u with respect to ui. You are going to get one weight function. Partial derivative of u with respect to ui plus 1. You are going to get another weight function. What is partial derivative of u with respect to ui? It is ni. Partial derivative of ui plus 1. Sorry, partial derivative of u with respect to ui plus 1. Partial derivative of u with respect to ui plus 1 is ni plus 1. So ni plus 1 are the weight functions when you are adopting the Galerkin method for this kind of element. Shape functions, or you can also make a note when you are adopting Galerkin method. When you are adopting Galerkin method in conjunction with finite element method. Okay. When you are adopting Galerkin method in conjunction with finite element discretization, you can say weight functions are same as shape functions. So please make a note of it. This is very, very important point. Weight functions are same as shape functions. Any questions here? So please make a note of all these points, and because we will be again coming back to these whatever I mentioned later as we progress. Any questions? So let me see any comments. And if there are no questions, let me summarize whatever we learned in the last two classes, as well as whatever we discussed in today's class. Advantages of finite element method. And it also answers some question which is asked by a student in yesterday's class. At the end of yesterday's class, a student asked some questions. It answers those questions as well, whatever is written here. Advantages of finite element method. And whatever we discussed, based on that, you can make these conclusions. As the number of elements is increased, the finite element solution gets better, even with fairly simple trial solution over an element. Fairly simple trial solution over an element. What is the meaning of that? Please note that previous problem we started with linear trial solution. You cannot have a trial solution simpler than a linear trial solution. You cannot have a constant. You will not be able to capture anything if you start with a constant trial solution. So linear trial solution is the simplest one. Okay, so that is what is written here. As the number of elements is increased, the finite element solution gets better, even with a fairly simple trial solution over an element. A simple trial solution obviously requires less effort. A simple trial solution obviously requires less effort in carrying out integrations and differentiations. When you have linear equation, something is linear, when you take derivative of it, you are going to get a constant. So your when the trial solution is simple, to do all these integrations and differentiations becomes less complicated. Okay. And second point, generally with approximate methods, when we say approximate methods, it includes both classical approximate solution techniques as well as finite element method. Generally, with approximate methods, the solution itself converges fairly quickly. However, the derivative converges much more slowly. So that is what is shown here. What is the trend that is being observed when we are solving this problem. The solution is converging much faster than the derivative. So that is what is mentioned. Generally, with approximate methods, the solution itself converges fairly quickly. However, derivative converges much more slowly. And when you are using lower order trial solution, this becomes even worse. Using lower order trial solution over an element, for example, a linear polynomial, as was done in this example, means in the previous example, makes this situation even worse. For this linear element, the solution is continuous over element boundaries, but its first derivative has discontinuities. I hope this statement you are able to understand, because we discussed enough on it. For a two-node element, the solution is going to be piecewise linear, whereas derivative of solution is going to be discontinuous at the element edges. Thus, a very large number of lower order elements must be used if the goal is to get good. If the goal is to get a good derivative solution. What do you mean by derivative solution? If you want to get good approximation for strain, good approximation for stress, if you are using linear elements, you need to use more number of elements. And what is the alternative for this? Of course, using higher order polynomial trial solution would alleviate this situation. Okay? This answers the question which is posed by a student in the last class. Anyway, we'll discuss more as we progress in the course. Okay. And whatever statement that is written here, unless you get a physical feel, unless you solve a problem, you will not be able to get a feel for it. So we will illustrate this point later using even higher order elements. Okay. So as we progress in the course, you will understand this much better. And the third point, with physical nature of unknown parameters. What is meant by physical nature of unknown parameters? A0, A1 are replaced with UI plus 1. It is easy to apply essential boundary conditions. Let me give explanation on this third point. You can see here what we have done. You can see here what we have done. Once we have the discretization, and once the problem statement is given, once we know where the essential boundary condition is applied, we need to just simply see what this which node corresponds to x is equal to 0. At that node, whatever value of you just equate it to 1. That is as simple as that. That is what we have done here. In this discretization, one element solution, U1 is taken as 1. In two element solution also, U1 is taken as 1. And what about the other boundary condition? What about the other boundary term? Here, these terms. X is equal to 1. X is equal to, this is nothing but U evaluated at X is equal to 1. And this is nothing but U square evaluated at X is equal to 1. So we need to see what X is equal to 1 corresponds to. X is equal to 1 in case of one element solution, it is nothing but second node. And in case of two element solution, it is nothing but third node. So we just plugged in that one. That information we plugged in here. Wherever U1 is there, replaced with U3. Wherever U square or U1 square is there, that U evaluated at X is equal to 1 square is there, we replaced with U3 square. So why, how it is possible? Because now these mathematical unknown coefficients are replaced with some quantities which have physical meaning, so that makes it easy to apply the boundary conditions. So that is what is mentioned here. With physical nature of unknown parameters, it is easy to apply the essential boundary condition. That is another advantage of finite element method. What about the fourth one? The variables at the nodes must be selected in such a way that essential boundary condition can be imposed directly. In the sense, suppose you want to apply, or here, let's read the further, the second sentence here. Thus, for a fourth order problem, it is necessary to choose solution as well as its first derivative at each node as unknown nodal parameters. Fourth order differential equation or fourth order problem. Usually in structural mechanics, that corresponds to a beam problem. Beam bending problem, the governing differential equation is going to be fourth order equation. And for a bar problem, governing differential equation is going to be second order equation. Okay. So in case of bar problem, the variables, unknown quantities are nothing but displacement in each of the nodes. So the variables at each of the node is selected as displacement. In case of fourth order problem, which is nothing but a beam bending problem, the unknowns are displacements, transverse displacement as well as slope. So we need to select two variables at each node to be determined. Okay, that is what this fourth point is mentioning. Anyway, as we progress, you will understand this better. Okay, any questions here? 1, 2, 3, 4. And one more point is that, these are the 4 points. These are the 4 advantages that you have finite element method over classical approximate solution techniques. Any questions here? Any questions? I don't know you are following or not. Any questions? Okay, so let me, or we can make a note of what are the basic steps involved in finite element solution procedure. Okay, what are the basic steps? We'll quickly make a note of these basic steps, and once we solve a problem, we can come back to these basic steps and see whether we covered all these basic steps or not, and then you will understand better. Okay, so what are the various steps in a general finite element solution procedure? So please make a note of it. Any questions? So first step is discretization. You please make a note in your notebook, okay? First step in finite element procedure is discretization. Discretization in the sense, given domain, you need to divide into small elements. How many elements you need to divide? That depends on whatever accuracy that you are looking. Okay, so discretization. So we will, whatever is written after this, we will come back to this, then you will understand better. So first step is discretization. Second step is derivation of element equations. Derivation of element equations. So please make a note of it. And each of the element, you divided the entire domain into number of elements. So now you go to each element and write the trial solution, and then get all the quantities. Okay. Derivation of element equations, and then assembly of element equations. Each of the elements, you get, for each of the element you get equations, and all these element equation needs to be assembled. Assembly of element equations. So once you get the element equations, you assemble them and get the global equation system. Global equation system. And after you get the global equation system, you apply the boundary condition, introduction of boundary conditions. And once you introduce the boundary conditions, then you are ready to solve the equation system, solution of global equation system. And once you solve the global equation system, you are going to get the nodal values or nodal parameters, the value of the solution, approximate solution at each of the nodes you will be able to get. Once you get the nodal values or nodal parameters or the solution at the nodal points, you go back to each of the element. You go back to each of the element, and then you try to get the solve for the solution in each of the elements separately. And then once you have solution in each of the element, you can actually do some plotting of the solution in each of the element, and you are going to get the entire solution. Okay, so these are the basic steps that are involved. These are the steps that are involved in a general finite element procedure, and we will see one example, then you will understand better. And please note that whatever problem that we looked at, in the last 2 classes, we did not follow in these steps. Okay, we did not follow these steps, but we solved the problem. But now we redo this example. We redo this example following those steps. So then you will understand. Okay, and please note that we are taking small steps from classical approximate solution techniques to understand finite element method. So this learning process is going to be gradual. Okay, so it's not going to be one step. If you take a jump, then your understanding may not be proper. So that's the reason we are taking small baby steps and try to understand what this finite element method is. So that is what we are doing. So now we'll take the same example and follow this and see whether these steps, following these steps, what is the procedure. Okay, so let's look at the same example. Let's look at the same example. Please take a note of this in your notebook. Same boundary value problem. Okay, and this is a typical element. And you can see here something is written. I'm going to explain to you. What is the typical element? Typical ith element that we looked at in the previous classes. Typical ith element. The first node is going to be the one of the node is going to be ith node. Another node, typical ith element is going to connect ith node to I plus 1th node. That is what is shown. What is this I? I is nothing but, you can say, global. It's a global node number. In the sense, there are several nodes are there. I'm referring to the ith element, ith node and I plus 1th node. That's why it's called global node number. Okay, global node number. And this ith element, this is the first node and this is the second node. And first node location is x1, second node location is x2. And length of this element is L. Length of this element is L. Okay? This I and I plus 1 are the global node numbers. So now what I am going to do is, I am going to introduce some local coordinate system. Local coordinate system. First node, I'm going to number it as 1. Second node, I'm going to number it as 2. This is a 2-node element. First node is numbered as 1. Second node is numbered as 2. And what is the relation between local node number and global node number? Local node number local node number 1 corresponds to global node number I. Local node number 2 corresponds to global node number I plus 1. Okay? Local node number 1 corresponds to global node number I. Local node number 2 corresponds to global node number I plus 1. That is the correspondence. That is the relation between local node number and global node number. Okay? And similarly, this node, first node, ith node, what is its position? It is x1. I plus 1th node position is x2. What is this x1, x2? What is this x1 and x2? They are in the global coordinate system. Global coordinate system. In the global coordinate system, the position of this node is x1, this node is x2. Similarly, I want to define a local coordinate system. Local coordinate system for this element. Local coordinate system is defined in such a way that first node corresponds to -1, second node corresponds to 1. Please take a note of this, whatever I'm saying. You please take a note of all this information in your notes. And please note that each of these concepts, each of you as an individual have a different way of understanding things, okay? So whatever way it is easy for you to understand, you please take a note of that in that manner, okay? It is not necessary that the way you understand may be different from the way the other person may understand. It's not necessary that all should have similar kind of understanding, like, kind of technique. Anyway, that is all side information. So this node 1, global coordinate is x1, node 2 global coordinate is x2. Node 1 local coordinate is -1, node 2 local coordinate is 1. And the local coordinate system, global coordinate system is denoted with x. Global coordinate system is denoted with x. Local coordinate system is denoted with s. Okay? It's like same point, the same position. Some point is there in space. Same point is being referred in the global coordinate system separate in a different way, and local coordinate system in a different way. The point is same, that particular location is same, but in local coordinate system it is -1, and in the global coordinate system it is x. It's similar to your similar to your like your official name and some nickname. You may have some nickname at your home, but the same person. When we refer either using nickname or the official name, it's the same person. Similarly here, the same point. In the global coordinate system, its position is x1. In the local coordinate system, its position is -1. And this point in the global coordinate system, it is x2. And the local coordinate system, it is 1. Any questions here? Any questions here? So why I am doing all this? You may ask, why are you bringing all these things? You teach finite element method. Why are you telling all this? It's not like that, okay? Please note that I told you, when you are discretizing, all the elements need not be of same length. All the elements need not be of same length. If all the elements need not be of same length, can we map all these elements? Can we map all these elements into a parent element? Anyway, all the elements have only 2 nodes. Only thing is their length is different, and the position of the nodes may be different. So why so many elements? Why not we map all these elements into a single element, a parent element? So that is what this parent element. This S coordinate system, whatever we are using, this S coordinate system, that is nothing but parent coordinate system. This is nothing but parent coordinate system. S coordinate system is parent coordinate system. Okay, so now I want you to do a small this one algebraic manipulation. So now x1, or let me say, you please make a note of this, okay? X is equal to x1. X is this one. X is equal to x1 corresponds to S is equal to -1. X is equal to x2 corresponds to S is equal to 1. Okay? Then what is the relationship between X and S? Is it clear? X1 corresponds to S is equal to -1. X2 corresponds to S is equal to 1. Suppose I have some other point, intermediate point. Definitely I am going to have some intermediate point. There are going to be infinite number of points between x1 and x2. So if I take an intermediate point, if I take an intermediate point in the global coordinate system, what is position in the local coordinate system? What its position in the coordinate system which goes from -1 to 1? So that is what I am interested. Is it clear? So x1 is mapped to s is equal to -1. X2 is mapped to s is equal to 1. So now what is the relation between x and s? What is the relation between x and s? That relation is not so complicated as you may be imagining. Okay, you need to go back to your basic coordinate geometry. And what is the equation of a line joining 2 points x1 y1 x2 y2? What is the equation of a line joining straight line joining 2 points x1 y1 x2 y2? Just go back and recall. If you are immediately, if you are able to recall, it's fine. If you are not able to recall also, that's fine. You please make a note of it. Equation of a line, straight line joining 2 points x1 y1 x2 y2 is given by y minus y1 is equal to y2 minus y1 divided by x2 minus x1 multiplied by x minus x1. Please make a note of it in your notebook. Y minus y1 is equal to y2 minus y1 divided by x2 minus x1 multiplied by x minus x1. Okay. So now, in the if you had noted that equation, whatever I just dictated, if you had noted that equation, now wherever y is there, okay, you replace y with s. Wherever y1 is there, you replace it with -1. Wherever y2 is there, you replace with 1. Wherever x is there, you retain it as x. Wherever x1 is there, you retain it as x1. Wherever x2 is there, you retain it as x2. Is it clear? If you simplify that equation looks like this. So that gives you relationship between the local coordinate system and global coordinate system. Any questions? Please take a note of this. Any questions here?
Excuse me, sir. Sir, can we say L will be equals to 2?
That is L is equal to 2 only. What is that to what is there to say? That is L is equal to 2 only. L is equal to 2. L is equal to 2 in the map, in the parent element. L is equal to 2. They have a length. This actual element is there. You can make a note. Actual element and parent element. Actual element is being mapped to a parent element which is of length 2 units. Okay.
But sir, in question it is written x from 0 to 1. No?
What x from 0 to 1? Why are you confused? Why are you bringing all that? You focus on this portion. I'm telling you. I'm talking about global coordinate system, local coordinate system, mapping I'm talking, and you are talking about this one. You first focus on this. No. I don't know what you are talking. Understand? I am talking about a typical element. I am talking about a typical element whose first node is x1, second node corresponds to x2, and whose first node in the global coordinate system it is I, whose second node in the global coordinate system it is I plus 1. Such element I am talking about, and you are talking about this one. No,
Okay, okay, sir. Yes, sir. Yes, sir. Yes, I got it.
That is irrelevant, okay, at this stage. Okay, I am saying you focus on this. You focus on this. Any other questions? So is it clear, this mapping, this equation, how this equation is obtained? How this equation is obtained, it should be very clear to you. This equation is nothing but it's coming from linear interpolation. Linear interpolation is nothing but equation of a straight line joining 2 points x1, y1, x2, y2. Y minus y1 is equal to y2 minus y1 divided by x2 minus x1 multiplied by x minus x1. Based on that, you can easily write this. Wherever y is there, you replace with s. Wherever y1 is there, you replace with minus 1. Wherever y2 is there, replace with 1. And then see whether you are getting this equation or not. What is the use of this equation? What is the use of this equation? This equation gives us a relation between the local coordinate system and global coordinate system. What is the relationship between local coordinate system and global coordinate system? We just check. When I say this is the relation between s and x, don't immediately take it for granted. You please cross check. No, you please cross check. If you substitute, if you substitute x is equal to x1, if you substitute x is equal to x1 here, what is going to be s value?
-1.
That corresponds to this. And when you substitute x is equal to x2, when you substitute x is equal to x2, s is equal to what? It's going to be 1. So this relation is, mapping is correct. In the sense, this relation, there is no mistake in this. You need to cross check like that. Or other way, you can do another way. You substitute s is equal to minus 1 here. You substitute s is equal to minus 1 and try to back calculate what is x. X you should get as x1. When you substitute s is equal to 1, you should get x. When you try to find what is x, it should be x2. So this relation is connecting. This relation is connecting local coordinate system to the global coordinate system. Okay? And if here it is written s in terms of x, s is written in terms of x. If you don't like it, if you want x in terms of s, you rewrite this. You invert this, you get this one. X in terms of s. Okay? And now, if that is clear, how this element is actual element. Actual element is going from x1 to x2. That element I am mapping to a parent element going from -1 to 1. A parent element having 2 units length. Parent element length is 2 units. Okay? It's like a rubber band. You can imagine this rubber band, or you imagine this is one a point, this is another point, and you are stretching a rubber between these 2 points. Okay? Imagine this is like a rubber band. Stretch it between this point and this point. And this length of this rubber band is L, but I want to map this. I want to map this onto another element or parent domain. I want to map it to a parent domain where this corresponds to -1, this corresponds to 1. Okay? Anyway, just think about it. Now you have actual element being mapped to a parent element. parent element is 2 units in length. And now, just now we got a relation between local coordinate system and global coordinate system. Now I'm interested. If I take a small element, if I take a small element here in the x coordinate system, if I take a small element of length dx, small element of length dx in the x coordinate system, what it corresponds to in the local coordinate system? What it corresponds to in the what it corresponds to the actual element. I want to know what is the relation in a way. I want to know what is the relationship between dx and ds. What is ds? ds is nothing but a small element in the parent element, a small length in the parent element. Okay, this parent element is having two units length. I'm taking a small piece of that ds. If ds is the size of the element that I take in the parent domain, and what it corresponds to here in the x coordinate system, what is the relationship between dx and ds? This relation is very, very important. Okay, so how do you get this? How do I get it? You just take you take differentiation on both sides of this equation. You take if you take differentiation on both sides, it's going to be dx is equal to L is a constant, ds divided by 2, or L by 2 ds, L by 2 ds. And x1, x2 are the coordinates, so they are constant. So these two, when you take derivative, they are going to be 0. So this is the relation between dx and ds. Small differential element in the actual element, how it relates to the small differential element in the parent element. So this relation, you take it, and if you want to write, you can write it in this manner. And this is what is called, this is please note that dx is equal to L by 2 ds, or you can write it as dx divided by ds, dx divided by ds. I think time is running out. I need to stop the lecture. I will discuss more in next class. Okay, so dx over ds, and if you invert it, you are going to get this. So please go through all this. We'll discuss further in tomorrow's class. Let me take attendance. Okay, thank you.
Thank you.
Thank you. Thank you, sir.